Welcome to our discussion on solutions of exponential equations, i.e. applications of the exponential and logarithmic functions. So we're going to learn how to solve exponential equations, how to solve exponential growth or decay equations when sufficient data are given, and how to solve exponential equations that represent demand, supply, total revenue, or total cost, again, when sufficient data are known. So the first thing we want to try and figure out is how to model and solve problems involving Gumpertz curves and logistic functions. Okay, so let's look at solving these things. An equation in which the variable appears in the exponent is called an exponential equation. Logarithmic properties are very useful in converting this type of an equation to one that can be solved easily, i.e. it's a way of peeling that exponent down out of it and putting it on the line, basically putting it down in the equation where we can solve for it as if it was just a regular old variable. So for instance, if we want to solve something like this, the whole point is we need to get x all by itself. We need to peel off all of its layers, working from the outermost layer. So the first thing we do is we undo this multiplication by dividing, right, on both sides. Now we've got 25 raised to a power of, 2x. We need to peel off that exponential function, and what undoes an exponential is a logarithmic, and we can choose any log that we want. Normally we'll choose natural log just because everybody has a natural log button and it's easy to use. So we normally use either natural log or base 10 because those are usually the only two buttons on calculators. Natural log even being more popular than the log button. But in any case, you could do log of both sides, base 10 if you wanted to. When you take the log of something, remember it undoes the exponential power. The power comes down in front, and this becomes multiplication of 2x times natural log of 25, which is just a number. Natural log of this is just a number. So again, to solve for x, we need to peel away what's left, which is multiplication of these two things. So we divide by those two things, and we get x equals 1.75 when we round. And that's it. That's the basic set of steps to solving any kind of exponential function. Whatever you have, you need to isolate just the a to the x, right? You need to isolate the base thing that's being raised to a power. Once you have that, it's these same steps. You take logs of both sides, either natural or regular logs, then divide out by the numbers so that you get the variable all by itself. Here's another example. First thing we do, divide both sides by 6. Then we take the log of both sides, which, this stuff comes down, divide both sides by the log to isolate x further. Now we have this, so we would add 2 to this side and then divide the whole thing by 3. Remember, this is a number, so you could just put this in your calculator and get a number, then add 2 to it, and then divide it by 3, right? So here it is plus 2 times 1/3. If you do it like this, then you can put it in your calculator without having to round, and you can get the most accurate answer possible, which is what we always want to strive for. Okay, how about growth and decay? Exponential decay models are just those that have the following constraints, right? That it's got the general function of f of x equals some constant times a, your base, raised to the negative x, where a is bigger than 1, c is bigger than 0, i.e. positive, and we could rewrite it as b to the x, where b is a fraction between 0 and 1, and c is still positive. Both ways work. So a company finds that its daily sales begin to fall after the end of an advertising campaign, and the decline is such that the number of sales is modeled by 2,000 times 2 to the negative 0.1x, where x is the number of days after the campaign ends. You can see right off the bat this means they started with 2,000 sales, because if x is the number of days after the campaign ads, then when x is 0, that means when the ads come out, they started with 2,000. Because if you put in a 0 for that, you get 2 to the 0, and anything raised to 0 is 1, and you just get 2,000. And then they just start going down from there. How many sales have we made 10 days after the end of the campaign? Well, that's easy. You just plug in 10 for x. You get 0.1 times 10, which gives you negative 1, which gives you 1/2. And then you get 1,000. And then if the campaign does not want sales to drop below 350 per day, when should it start a new campaign? All right, so here's the solution for the first one, where we need to get, we put in, 2 to the negative 1, we get 1,000. Easy, easy. The second one, though, we need to solve kind of backwards. We need to put a 350 in for here and then figure out what power of x gives us that. So we peel off the outer layer by dividing by 2,000. Gives us this. Then we apply a log or a natural log to both sides, which brings the power down in front. Then divide both sides by that log base 2 to isolate it. Then divide both sides by the negative 0.1 and get roughly 25.15 days, right? So sales would be 350 at day 25.15, or basically the 26th day after the campaign. So that's when they should then hit them with a new campaign. If a new campaign isn't begun on or before the 26th day, sales will drop below 350, and they'll continue to drop. If we graph the function, we'll see that they'll eventually level off at just barely above 0. I mean, they'll get to a point where there'll be a fraction, and then that fraction will be small enough that you'll just round down to 0. The function itself never actually reaches 0, but if you round it, you can round it down to 0. Now, many applications like business, econ, biology, social sciences, things like that, they can describe the growth of money, bacteria, or any kind of population using these exponential growth models. Again, with the same properties that C has to be greater than 0 and A has to be bigger than 1. For instance, this right here represents population growth for humans, insects, or bacteria. It also represents continuously compounded interest, so growth of money. With those economic and management applications, we can see that sometimes cost, revenue, demand, and supply can also be modeled by exponential or logarithmic functions or equations. So for instance, suppose the demand for a product is given by this. P equals 30 times 3 to the negative Q over 2, where Q is the number of thousands of units demanded at a price of P dollars per unit. Then the graph of the demand curve is given by this. We can see that it's a exponentially decaying function because it's going down. So the demand function is given by this. At what price per unit will the demand equal 4,000? So remember, demand is Q and price is something else. How many units, the nearest 1,000 units, will be demanded if the price is 1732? All right, so the first one is easy because 4,000 units means Q equals 4, because remember we were told that Q was in thousands of units. So then we just plug in 4 for our Q and calculate it out, and we get $3.33. Easy peasy. When we want to go the other way, that's when we have to do the extra steps to solve for the variable that's stuck as the power, right? We have a price of 17.32. First thing we do is we peel off the 30 by dividing by it, right? We're isolating the exponential. Now that we have the exponential all by itself, we apply a natural log or a log to both sides to peel off the actual power, which is negative Q over 2. Then isolate the variable further by dividing by natural log of 3 and multiplying by negative 2. And thus we get Q equals all this junk. Throw it into your function, throw it in your calculator, and you get that it's basically 1. And so the demand would be roughly 1,000. Okay, let's look at these Gumpertz curves and logistic functions. What the hell is a Gumpertz curve? Well, it's a family of curves that's been used to describe human growth and development, the growth of organisms in a living environment, and the growth of many types of organizations. And it's called Gumpertz, named after the dude who, first discovered it or came up with it. So these curves are graphs of the equation of the form n equals c times a to the r to the t, right? So instead of r times t, r is being raised to the power of t, where t represents time, r is a fraction between 0 and 1, and it's a constant that depends on the population. A represents the population of the proportion of initial growth, and C is the maximum possible number of individuals. and then n is the number of individuals at a given time. And the reason why c is the maximum number is because as t goes to infinity, right, as time goes to infinity, we have a fraction raised to a really big number. As we raise fractions to larger and larger numbers, they get closer and closer to 0. And in fact, if you take the limit as t goes to infinity, r to the t becomes 0, a to the 0 becomes 1, and the number of things just becomes c. So here's a typical example. This is used to predict the size of a deer herd introduced on a small island. Here we can see the maximum number of deer would be 100, and we can figure out the maximum based on how much area they have and how much food they have, how many predators they have, that kind of stuff. The proportion of the initial growth A is 0.03, so that's basically how fast it's growing at the beginning, and R is 0.2. For this example, T represents time measured in decades. The unit of measure can always change from these things. It can be seconds, hours, minutes, years, decades, whatever. The graph of this function is given below. You can see that it levels off because, like I said, as t gets bigger and bigger and bigger, you're raising a fraction, or in this case a decimal, to a larger and larger power, which makes it get closer and closer to 0, which means this raised to 0 gets closer and closer to 1, which is why the whole thing gets closer and closer to 100. A hospital administrator predicts that the growth in the number of hospital employees will follow the Gumpertz equation with 2,000, blah, 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 right? What is the number of employees when the facility opens? Well, t represents the number of years after opening, so the facility opens when t equals 0. If we plug a 0 in to t, we get 0.5 to the 0, which is just 1. Then we get 0.6 to the 1, which is just 0.6. So we're basically just taking 60% of 2,000. How many employees are predicted after 1 year? Well, that's when we put in a 1 for t, and then we have to figure out what 0.6 to the 1/2 power is, and then multiply that by 2,000. We can graph the curve using technology, and then the maximum value of n that the curve will approach, well, that's easy. Remember, that's always the number in front of it. That's the 2,000. So we'll see, right? Plug in 0 becomes a 1. We take 60% of that. They started with 1,200 employees. In 1 year, that's in, not natural log, in 1 year, t equals 1. So we plug a 1 in there, 0.5 to the 1, right? Which is that's just a square root. Take the square root of that times, and we get roughly 1,549. So after 1 year, we went from 1,200 to 1,549. We can graph the function, and we know that 2,000 is the asymptote. It's also the number that's in front of it, and we know that 2,000 is the maximum possible value for employees, right? You're going to have a maximum number of employees because you just don't have enough space for them at some point. How about logistic functions? Well, Gumpertz curves describe situations in which growth is limited. There are other equations that model this under different assumptions. 2 examples are given. We've got y equals c times 1 minus e to the negative ax, where a is greater than 0. And we can see that when we graph that, we get something that looks like a Gumpertz curve. It also looks like a log. We also have this funny curve. And you can see that it ends up trending and looking like a log curve at the end, but it initially looks like an exponential, right? It grows really fast, and then it flips over and starts to grow slower. So it grows exponentially and then logarithmically in the end. These equations have many applications. In general, both A and B can be used to model learning, sales of new products, and population growth. It would make sense in all those, right, that you could learn something really fast in the beginning, and then your learning starts to trail off because, once you start to master something, there's less to learn. Same thing, sales of new products, right? There's all the hype in the beginning. Everybody wants everything, right? They want the new iPhone as soon as it comes out, and then after a while, those sales start to taper over. Same thing with population growth, right? Populations always grow exponentially, but because of limitations on, food sources and space, that growth can tend to taper over and become logistic. Now, with human population growth, that normally doesn't happen because, we can overcome those limitations. But when we talk about population growths of animals, they are constrained by those two things. And so this function is called a logistic function, and the graph is called the logistic curve. And that's all I got for you guys.